presentation, I will continue talking about symbol-based knowledge representation. So today we're going to be looking at scripts, at rules, at confidence factors, expert systems, and an attempt to develop a fundamental knowledge representation language. So let's start off with scripts. So they were designed to represent knowledge about events, i.e. things that extend in time. They were used to demonstrate newspaper story understanding, and they were developed by Schenck and his colleagues. You should remember Schenck from the Searles article, Minds, Brains, and Programs. So let's have a look at them. And so there are several aspects to scripts. They have a name, they have a track, but most importantly, they have props, roles, entry conditions, and rules. So the props are things that we might expect to see in a coffee shop: tables, menus, food, check, money. Same thing with roles. We have customers, cooks, owners, waiters, and cashiers. So these things help retrieve the proper script. So you have a newspaper story, you scan it, you do a keyword search on any of these items, and if they show up with a certain frequency, and also depending on how many show up, you would retrieve this script as a possibility for understanding or processing a newspaper story. We additionally have entry conditions and results. So in this particular example, the customer is hungry, although I think you don't necessarily have to go to a coffee shop to be hungry. You might want to socialize there too. Customer has money, or maybe your friends have money and invited you. Customer has less money, customer is not hungry, owner has more money. So yeah, ideally, right? So these things help to determine the newsworthiness of a story. You know, if you have a newspaper story, typically there's something that is of interest. So how do we determine what's of interest, what's unusual, what's newsworthy about a story? So eventually we will use these things to determine, say, expectation violations. All right, so very helpful, right? So then we have different scenes that correspond to things that typically happen, events that typically happen in a newspaper story or in an event that extends through time. So in this particular example, we have 4, and so let's go through them one at a time. So we have the scene of entering. Customer goes into the restaurant, they look around, they decide where to sit, they go to the table and sit down. And so ordering, customer picks up a menu, maybe not, maybe they just know what they want anyway. If you're a good customer, a lot of times the restaurant or the servers, they already know what you want, and they might even bring it to you. That happened to me once, where I showed up at a restaurant, I washed my hands first, and by the time I sat down, I mean, the waiter sort of like put in the order what I typically order anyway. So a little bit of a risk, but they kind of knew me enough. So in any case, the customer orders food from the waiter, tells the waiter tells the cook the order, and the cook prepares the food. So again, in the story that I told you a moment ago, what was newsworthy about it is I didn't pick up the menu, I didn't decide on the food, I didn't order from the waiter. They all did that for me because they knew what I typically order in that particular restaurant. So helping us to determine expectation failures, violations, and so why is it newsworthy? So again, eating and exiting. So that's what they. So those are the scripts that they use to determine events or to capture or formalize events. Another thing that Schenck and his colleagues and collaborators try to do is to develop a fundamental language in which to represent things, in their particular example, events. And so they call it conceptual dependency. And so the idea was to reduce what we're saying to fundamental concepts. Notice that most AI systems represent knowledge in natural language, such as English. Even logic, first of all, logic is a formalization of a natural language, a lot of times English. So let's see what they did and review it and discuss it a little bit. So they have 4 primitive conceptualizations. So they're actions, they're objects, they're modifiers of actions, and they're modifiers of objects. All right, and these are the shorthands, ACT, PP, AA, PA. So then they have these modifier of actions. So notice there is a trans for an abstract transfer, a P trans for physical transfer, propelling something, moving something, grasping something, so moving a body part rather than physically propelling something or physically transferring something. And we have a mental transfer, we tell something, we have a mental build, we decide something, we speak, and we attend. Okay, so let's see what that buys us. So here are some examples from their book, Computer Models of Thought and Language by Schenk and Colby. So how do you represent the sentence John ran? Now I should tell you that in addition to these fundamental concepts, they also have some sort of graphical representation that enables them to display how these things relate. The exact nature of these arrows is immaterial. We just want to understand the power and limitations of this conceptual dependency. So John ran. So John, there's a physical transfer. All right, that makes sense, right? Physical transfer or location of an object. Cool. John is tall. So John has a property, and the property is his height. Notice that this is not one of those conceptual dependency reductions. And the height is above average. All right, I can sort of see that. Okay. John pushed the cart. So John propelled something. What did he propel? The cart. Okay, got it. John ate ice cream. So John ingested something. What did he ingest? Ice cream. And so notice that now it gets to be a little bit different or peculiar. So how did he eat the ice cream? So there was a spoon, and the spoon involved in some doing by John. And the doing that John is doing with a spoon is to ingest ice cream. Now what's interesting is that the sentence doesn't mean that he ate ice cream with a spoon. And we well know that you don't have to use a spoon to eat ice cream. So this is a little bit tricky here. But here's the one that I always thought is sort of like a good example of why the system might not work that well. So Bill shot Bob. So what happened over here? So something got propelled by Bill, and what got propelled is a bullet. And the bullet came from a gun, and the gun was directed at Bob. And the consequence of all of this is that Bob's health is now -10. So yeah, now you know what it means to be, well, presumably dead, or we don't know whether he shot him dead or whether he shot him to the extent that he has to go to the hospital. So we don't know what health -10 is. We don't know what the range is of this value. So in any case, I think what is useful from this approach is the idea that there might be something of a fundamental knowledge representation language. Now notice that there are some attempts by existing software, the Stanford parser and other parsers use lemmatization to reduce a word to its canonical form. So that's not as intense, not as fundamental as what conceptual dependency tried to do, but it's in that same ballpark, right? If we look at neural networks, in particular word embeddings, then we know that a word is represented by a weight matrix. Okay, so again, not necessarily fundamental, but a different way of representing things. So that's, again, the reason I presented the conceptual dependency materials, or an excerpt of it, a very, very high-level overview, is to understand or to think about, should we have something of a fundamental knowledge representation language? We know that language is very important to us, to humans, because it enables us to express things. And the higher our command is of a language, the more we can express, the more subtle concepts or events we can express. So there's certainly this idea that language is kind of fundamental to thinking and to knowledge representation. But it seems that sometimes we're able to think things that we're not necessarily able to express in language. And so perhaps there is a a different way in which things are being represented in our mind, and then they're being translated into language. I do not know. I'm not an expert in these things. I'm simply raising this issue to you. Okay, so let's talk a little bit about rules. And so here's an example of what we want to talk about. Many times expertise is captured in rules. So this is a rule from mice in an expert system for diagnosing infectious diseases. These are sort of like from the 80s. So this example is from Buchanan and short-lived rule-based expert systems. So if the identity of the organism is not known with certainty, and the stain of the organism is gram-negative, and the morphology of the organism is rod, and the aerobicity of the organism is aerobic, then there is strong suggestive evidence, point 8, that the class of the organism is this one over here. So again, these are rules that capture knowledge. And this is not the sort of skill that I talked about when it comes to, say, playing the piano. This is domain expertise. So let's tease this apart here in the next couple of slides. The first thing we want to understand is that there are these things called confidence factors. So strong suggestive evidence is 0.8. So not super strong, it's not 100%, it's not 0.9, not 0.95, but it's strong. So the certainty or confidence factors have been used quite a bit. We have seen expert systems. We know about Watson using confidence or certainty factors. It makes sense to use these things because when we use language, we're not always sure, right? We use things like sometimes, always, once in a while. They're based on subjective experiences. So, for example, if out of 5 times I tried to start the car, the engine cranked 3 times, well, then perhaps we have a confidence factors of 60% when asked, does the engine crank when I try to start it? Okay. All right. So again, expertise is, we're not always 100% sure, right? We're sort of like, it sort of like seems like the more you know, the less you know, sort of thing. That the more we probe something, the more we realize that, well, maybe that is not entirely black and white. If you see a doctor ever so often, medical diagnosis a lot of times falls in this category. We're not 100% sure, but we'll sort of like take the best guess, right, and then treat it. So this rule over here has a confidence factor associated with it, but typically we chain rules along, and we'll see that here in a moment. So at some point in time, we have to combine these confidence factors. So let's see how we might be able to do that. So here's an example that comes from this Weka Studio tutorial. If the income is good and debt is low, then approved loan is yes, with a confidence factor of 0.7. Okay. So what we need to understand then is we have these premises, right? Income is good and debt is low. Well, how do we know what's our confidence and the income is good and the debt is low? This confidence factor is for the entire rule, but how about the premises? Oops, wrong way. And so suppose that income is good, we're kind of like, yeah, 60% confidence, debt is low, 80% confidence, right? So these are confidence factors. So how do we combine these confidence factors? So the confidence factor of the conclusion is the minimum of the confidence factors of all expressions in the condition part. So in this particular example, 0.6, multiplied by the confidence factor of the goal. So in our example, the minimum is 0.6. The confidence of the rule was 0.7. And so we multiply those two things and it gives us 0.42. Okay, so that's the confidence that we will approve the loan given our confidence in these two premises. So that's how we combine confidence factors in the premises. So we'll take the minimum. If we go over here, eventually we'll see some rules that have confidence factors. Well, we will eventually see an example where we have confidence factors associated with these things. So we have to have confidence in all of these things. and then we combine them in this way that we have seen with the confidence factor of the rule to get some new confidence. Now, suppose there are several rules that might shed light on whether we should approve a loan or not. So for example, if the market value of the property is high or very high, then the approval of the loan has a certainty of 80%. So suppose we actually determined that. Suppose it was 0.6, that it is very high. So we again multiply these two things together. So we now have 0.48. Now notice we now have 0.48 that we will approve the loan through this rule, and we have 0.42 through this rule. So what we're going to do now is we're going to combine this information. And so what we're going to do is we're going to add those two confidence factors, and then we're going to subtract the intersection. So 0.42 plus 0.48 minus the intersection, which gives us 0.7. So notice that we now have several pieces of data, like almost like a puzzle, that shed additional light on whether we should approve the loan or not. And so based on additional information, we now have a much higher confidence than we had before. So that's how we combine confidence. So let's have a look at expert systems, which were very popular in the 80s, and which are rule-based systems with confidence factors. And they sort of developed an algebra that we have seen over here a moment ago about combining confidence factors. So I think expert systems are going to come back, but in a different form. And so there were three key components of an expert system. There was the inference engine, which combined the rules and did the algebra. There was a knowledge base, and we'll have a look at that in a moment. The knowledge base primarily consisted of those rules that we have seen. And then, of course, a user interface. These things were designed to be really, really user-friendly. And so the user, typically a medical doctor, would describe a new case through the user interface and work with it for a while, and then get some sort of like advice and also explanations. So the idea is that the expert system we're going to be looking at is called MySyn. It was developed for infectious disease control. Now, a family physician might not be an expert in infectious disease control. So the idea is that they would consult this expert system rather than an expert, because experts might be in short supply. So in Sweden, for example, we have this course, CSSE 241, and we'll go to Sweden ever so often and work with some people at the University of Uppsala, which is primarily, well, it's a very big medical school. And so Sweden is not very densely populated outside of its big cities, and so doctors that work in rural settings don't always have the expertise for some of the stuff that they have to deal with. And so rather than calling up a doctor at Uppsala or some of the other medical centers, they actually did develop some expert systems that help those doctors diagnose certain diseases. Now, eventually, the people around MySyn developed eMySyn. So eMySyn is everything that you see over here except for the knowledge base. And so there was actually a job description back in the 80s and 90s of a knowledge engineer. So the knowledge engineer would work with a domain expert to fill this knowledge base. And so notice that they had this backend, literally, a tool for building expert systems that enabled them to trace the working of the expert system, enabled them to fine-tune the confidence factors and the rules. So that was kind of the idea. The knowledge engineer would work with the domain expert to sort of like fill up this knowledge base and then fine-tune the system until they were happy with the way it was working. So here are some aspects, like zooming in just a little bit, about how to use this system. So the physician user, has this user interface that they work with. They will see a dialogue here in a moment. The system will ask questions. The physician user will answer them. But it was very important to them that the physician user was confident that the system was working properly, because in the end of the day, they are the ones who are concerned with the actual case, with the actual patient. They want to do right by their patient. And so there was a way to give explanations. We already have seen this one over here. So in addition to the rules that we have seen, there's also dynamic patient data that we store. And so that's kind of like an important aspect of it. Let's have a few more rules over here. Here's another rule, again from Rule-Based Expert Systems from the book. Here's a rule for a recommendation that is being made. So notice that they have that they can, in this particular example, have up to 5 recommendations, again with different certainty factors, right? As we have seen before, perhaps there's another rule that makes recommendations for some of these therapies, and so they would combine that information. Now notice that they go down fairly low, because as we have seen, sometimes it's important to have negative information. I mean, if the physician here so realized, geez, you know, really didn't come up with something stellar, that's important too. Just like IBM Watson, you don't just want to blurt out some answer. You want to understand that, yeah, I'm actually pretty confident that the answer is correct. So that's why it is important to go down, so that we don't just have no knowledge, but we sort of like have knowledge of how much we actually know, about the quality of our knowledge. So here is sort of like the beginning of a dialogue. And they ask for patient's name, sex, age. Again, have there been any cultures taken? And so the answer is yes. And so they ask, you know, from which site was it taken? So it turns out that the physician misspelled blood, so they corrected it. Again, just like giving feedback here, just like that things are, you know, that the system understands what's going on and just like blindly accepts information. There's a year. And so they call this thing culture organism 1, and some sort of like information about this thing. And it goes on quite a bit. I don't want to bore you with this stuff too much. So let's instead have a look at some aspect of expert systems that are designed to make it very, very transparent, and to a certain degree help probably a non-expert physician to eventually become an expert in the field. So for example, they ask us the question, the expert system asks the question, is organism 1 Streptococcus? And the answer is no, okay? And then the user can say, why did you rule out Streptococcus as a possibility for organism 1? And so what they do is they actually take those rules, and so I said, and display them, right? So you can sort of like see a little bit under the hood of these expert systems. So they say Rule 33 could have been used to determine the identity. However, Rule 2, Clause 2, was already known to be false, so was never tried. So that's pretty cool. So they use the expertise in the rules to explain to the user that yes, we couldn't have done that, or no, we couldn't have done that. How do you know? So we have why, how, and what, right? So over here, how, so like talk a little bit about the certainty factors and what. So I said we could have used, let's see, the rules listed below use whether the patient has this one over here. And then they ask, well, which rule do you want to see? And again, the system would display the rule. But I just want to highlight to you is that these were very, very powerful systems. They took a lot of effort to build, but they were very, very, very helpful to people. All right, so a little bit about how we might represent knowledge in a symbolic way. On Thursday, we're sort of going to review this a little bit and sort of like have a look at and review how neural networks represent knowledge. All right, I'll talk to you then. Bye.